Okay, Dr. Matthew J. Traum here. This is part two of the problem that we were previously solving for dynamics, looking at how to translate the equations of motion for a point that's in a reference frame that's both rotating and translating into the ground reference frame. So just a few little reminders from part one, if you happen to just be watching this video, part two all by itself. The first is the reference frame translation theorem, which is written here, which basically says that the derivative of some vector with respect to time in the ground reference frame is equal to the derivative of that same vector with respect to time in its own native rotating reference frame, that's reference frame A, plus the rotational velocity between the ground reference frame and the rotating reference frame crossed with the original vector itself. The rotational velocity between the reference frames, at least in our case, we're going to call this theta dot k hat. Remember that theta we define as the angle between the ground reference frame and the reference frame A, which is the one that's rotating. So theta dot is just the derivative of that angle with respect to time in the k hat direction, which comes out of the page. And then another reminder is we've got the product rule here, which is if you take a derivative of a product with respect to time, that derivative works out to be the derivative of the first term with respect to time times the second plus the first term times the derivative of the second term with respect to time. So it's just a reminder. And then the last little thing, this is just my little cheat to remind me that if we're doing a cross product, if I have I hat, j hat, and k hat, and they're all orthogonal to each other, if I do a cross, if I'm moving in the counterclockwise direction, that's positive, and if I'm moving in the clockwise direction, that's negative. And the way that I remember that is remember back to the right-hand rule. So if my thumb is coming out of the screen or out of the page in the positive direction, my fingers curl around in the counterclockwise direction, and so that reminds me of what positive is. So that's just a little trick that I'm going to use to keep track of the signs of these cross products when we get to them. Okay, so we ended last time talking about or finding an expression for the velocity of point P. Point P is the point of interest in the rotating and translating reference frame, and we found that the velocity of point P in the ground reference frame is equal to r dot I hat plus theta dot r j hat. So that's a result from the previous part of this lecture. So we'll just propagate this forward. And we've got the velocity, but what we're interested in now, we need all the equations of motion. So that includes the position, the velocity, and the acceleration. And acceleration, as we'll see, is particularly important because for Newton's laws of motion, you need the acceleration to write the equivalent of F equals ma. So we need to get the acceleration. So that's actually step 5 now in this process. So step 5 is we're interested in finding the acceleration of this point P in the ground reference frame. And we're going to do that by applying the reference frame translation theorem, which of course is this thing that I've written up here on the top of the page. Okay, so we're interested in the acceleration, and so the acceleration of this point P, which is a vector in the G reference frame, well, that's just the derivative of the velocity in the G reference frame with respect to time, and we actually know this expression, well, gosh, we know it both in the G reference frame and from the previous part in the A reference frame, and those two can basically be swapped once you know them, because they're both correct versions of the expression. So just to clarify this, I'm going to just stick an A up here because, well, it doesn't matter. They're interchangeable. But ultimately, because I want this to correspond with this guy. So now let's see if I can get them both in the frame here. There we go. Okay, so in this case, my B, vector B as in boy, is V as in Victor, and so I'm going to just propagate that all the way through my reference frame translation theorem. So this derivative then is equal to the derivative in the A reference frame. So I'm just copying this now. Derivative in the A reference frame of B, which in my case is V of point P in the ground reference frame with respect to T, and then I'm going to add omega G to A, so that's again the rate of rotation between those two reference frames, and this is going to be crossed with my original vector, which is VP, again in the G reference frame. So again, I've just literally copied this guy down here, and I've just substituted V in for B. Okay, so the next step then is to figure out what all these things are. So this is where things get a little dicey. So I'm gonna write this out. So the good news is that I already know what this V of P in the G reference frame is, because I solved for it in the previous part of the problem, which we did before. So when I encounter VP in the G reference frame, I can just write it again because I solved for it already. So if I were to write this out, I would say that the acceleration of point P in the G reference frame, which again, remember, that's my goal for this part, for step 5, that's just the derivative in the A reference frame with respect to time of this VP in the G reference frame, which is what? It's just this. So it's R dot I hat plus theta R j hat. Okay, so we've got that first term nailed. We're going to add to that this rotation term. So that's going to be, let's see, oh yes, right, I know it from up here, right, because I figured it out before. So that's just going to be theta dot k hat. And then this is going to be crossed with the same thing again. So I'm literally just going to copy it over again, and I'm going to put it in the parentheses so that I can do my my multiplication on it, and my distribution of the multiplication. Okay, all right. So we've got that. Let's since we've got a little room here on the bottom, let's just write this out one more line. So now I'm just expanding this guy. So let's see. This is going to be the derivative of this guy plus the derivative of this guy. Well, okay, I've got to do product rule here. So this is going to be R double dot, the derivative of the first. Whoops. Oh, no. The derivative of the first times the second. There we go. Okay. Plus the first times the derivative of the second. There we go. That's better. Okay. So we've got that term written out. A little mistake here, but we can ignore that. And then I've got to add it to this guy. I'm going to do here the derivative of the first. Give me one moment. Okay. There we go. Derivative of the first times the second plus the first times the derivative of the second. And there's actually, 3 terms here, right? There's theta dot r and j hat, and so ultimately you would expect an additional term associated with the j hat term. But remember, all of these pointing vectors, all these unit vectors, when you take their derivative with respect to time, they go to 0, right? So this term goes to 0, and then the terms that would have the derivative of j hat with respect to time also go to 0. I haven't written them; they would be here, but they basically cancel out anyway. So no need to propagate those forward. Okay, so I've got this first term written, and then let me do the second term. So this is where things get a little dicey because I need to do cross product. So I've got theta dot r dot, and I've got k cross I. Oh boy, okay, what's k cross I? Well, hey, I've got this little cheat up here. K cross I, if I start at k and I move to I, that gives me positive j. So this guy is going to be positive j, and then I'm going to add to that. I'm now working on the second term, so I'm going to have theta dot squared times r, theta dot squared times r. Okay, and then I've got k hat cross j hat. So I'm going to go down here, k hat cross j hat. Well, okay, so now I'm moving in the counterclockwise direction. The clockwise direction, counter to the positive direction. So it's going to give me I hat, but that I hat is going to be negative. So it's going to be negative I hat. Okay, so we've got a lot here. Let me get a fresh sheet of paper, and we'll write down exactly what we had before, so that we can keep working on it. So let's see, the acceleration of p in the G reference frame, which is ultimately what we're going for, is r double dot I hat. That other term, of course, goes away. So we've just got now plus theta dot r j hat plus theta dot r dot j hat plus theta dot r dot j hat plus theta dot squared r in the minus I hat direction. Okay, just to confirm for you, here's the previous page, and here's the new page, and with the exception of this term, which of course goes to 0, hopefully I've copied these all verbatim. I'm just checking to make sure I have. Yes. Okay. So I'm just copying verbatim onto this page, so that I'm giving you guys an honest account of where we're going from here. Okay. So I've actually now done the hard part, right, which is to go through and take that derivative and the cross product. And so now I've got to collect up like terms. So I want to collect like unit vector terms. I hat terms independent from j hat terms, so that I've got basically a pure vector representation of this acceleration. So the acceleration of my point P in the G reference frame. Okay, so let's just collect all the i's together. So I've got an I here, and I've got an I here. So this is going to be r double dot from this guy, and then it's going to be minus theta dot squared r from this guy, right? That's where the minus sign comes from. And then that's all going to be in the I hat direction. Yes. Okay. Good. And then I've got to collect up all the j terms. So I've got let's see, a theta double dot r j hat, and then hey, look at this. This is cool. I've got a theta dot r dot j hat plus a theta dot r dot j hat. So those are going to just combine together to give me 2 theta dot r dot, and both in the j hat direction. So we can just distribute that j hat unit vector over both of them. Okay, and that's it, right? That's my expression for the acceleration of point P in the G reference frame. So cool. It actually works out to be a relatively simple expression. So I'm going to put a nice box around this so that we can find it again if we need it. And the last kind of piece of the puzzle then is step 6. which is to apply Newton's laws. Step 6, apply Newton's laws to write the expression for the force, effectively the equations of motion, to move point P. So we're going to apply the acceleration that I just found using Newton's second law to write an expression for the force to move point P. Okay, so just as a kind of a quick reminder to get us back into the frame of the problem, I've got my point P, so I need to make a free body diagram, right? That's basically a free body diagram showing a force acting on point P. So I'm just going to kind of draw an arbitrary force here. So this is the force of the object, basically, that I'm attaching to that point to get the desired motion. And I'm just going to call that some force. And I'm going to turn things a little bit because remember, I hat was in this direction and j hat was in this direction, and k hat came out of the page. So let's see, we've got I hat, we've got j hat, and we've got k hat. And if I wanted to resolve this force in those directions, I would start from the same point, except I'm going to kind of move down in the j hat direction, and then I'm going to move down in the I hat direction. They're orthogonal to each other, so that has to be a right angle. But this is the resolution of that force in the let's see, in the j hat direction, and this is the resolution of that force in the I hat direction. Okay, so just to give us kind of a sense of what that combination of vectors would look like. So what we're looking for is the force in the j hat direction, the force in the I hat direction, based on this acceleration that we've just solved for. So I know that the sum of the forces acting on P are going to just equal a mass times the acceleration of point P. Again, I'm interested in the G, which is the ground reference frame. And so I know this expression, right? So I can just say that that same sum of the forces now in the I hat direction are just equal to the mass times A of P I hat. And I'm just breaking things down here. Force of P in the j hat direction is equal to mass times the acceleration of my point P in the j hat direction. There we go. Okay, so now I've got my two separate directional expressions for those forces. And all I really need to know is what these accelerations are. Well, hey, look, I've already got them, right? But I just need to break them down into I hat and j hat. So I know that the acceleration in the I hat direction it's just this first part of the expression. So it's r double dot minus r, theta dot squared, there we go, r in the I hat direction. And I know that A, and these are A of P, so A of P in the j hat direction is just equal to the second part. So theta double dot r plus 2 theta dot r dot in the j hat direction. Okay, right. So we got those. Now, last little piece here, I just have to take these expressions and plug them into these expressions, and that tells me the force that I have to put on point P. So remember, this is point P. This force that I have to put on point P to get it to accelerate in this reference frame, effectively. So let's see. The force of point P in the I hat direction is just going to be the mass of wherever we're sitting in point P multiplied by this I hat acceleration. So it's r double dot minus theta dot squared r, okay, in the I hat direction, and then the force that's acting on point P to affect this motion in the j hat direction is just that same mass of the system multiplied by this term, which is theta double dot r plus 2 theta dot r dot in the j hat direction. Okay, so those are my expressions for the force based on some mass of the system and the acceleration that I've solved for, which will induce motion in point P. Now, the thing that I really want to point out here, hopefully you guys can see, I'm switching to a red pen to kind of accentuate the point, but notice that we've got a second derivative in this term of r, where r is the linear displacement of point P, linear displacement with respect to the g, the ground reference frame, and then here I've got the derivative of theta, where theta is the rotational displacement of point P with respect to the ground reference frame, right? So I've effectively got a linear acceleration in this term, and I've got a rotational acceleration in this term, and that's really key, right? That's sort of my sanity check to make sure that this is right, because ultimately these two terms are accelerations, and if I did not have that second derivative appearing, I wouldn't have a complete picture of the equations of motion for this point P. So that's just my check that I do have those two acceleration terms, and I need both of them, right? Because if I don't have one term and I have the other term, I'm missing a key component, either the linear translation or the rotational component of the motion of point P. So the final thought here, just to wrap things up, is to remember then that if I'm interested in the equations of motion, well, I've already got them, but the reason that I need both of these expressions is, of course, if I've got the acceleration of point P, if I take the derivative of that, sorry, not the derivative, the integral of that over time, well, that's just going to give me the velocity of point P. And then if I take the integral of the velocity over time, that gives me the position, right? So this is the part that's sort of key, is if I don't have these terms and I start integrating, when I end up with the velocity and ultimately the position, I'm going to lose some information about the acceleration and therefore the velocity and therefore the position of point P if I don't have these two different accelerations, one in the I hat and one in the j hat direction. So just kind of want to point that out as a additional sanity check to add kind of an iota of completeness to this problem. So anyway, that brings us to the end of part 2 of this derivation. We now have the full equations of motion for point P, which again is a point that can both rotate and translate. It's fixed to an object that can both rotate and translate in a ground reference frame. So now we've got all the equations to describe the motion of that point on that object. So anyway, that's it. Thanks for your attention. Hope to see you guys in the next video. Bye.